Hello and welcome everybody to my talk called Scooby Ram, Where Are You? I like colorful graphics and those displays are really nice in here, so I'm enjoying those. But my name is Andrzej Grzesik. I go by Ax because if you're Polish, saying Andrzej is very easy, but if that's complicated, you can call me Ax and that works absolutely fine. I'm a co-founder of a startup called Datalinks, which is trying to solve contexts in the AI space, which is a very funny problem to approach. I have a Twitter, I have an email. If you would like the slides, drop an email, happy to share. A couple things about me. I associate myself with those icons. So I'm a Java champion, a JavaOne rock star from the Moscone times, and I'm involved in Polish Java user group, conference called GeekOn, and some other things. And I live in London. And I, throughout the presentation, use dry jokes, primarily as a reminder for myself to drink, because otherwise the throat will run dry and that's suboptimal. So, some people know Nitsan, and Nitsan said that. Obviously, I am not at Nitsan's level, but I can quote Nitsan, and that makes you smile, and that is already great. And yeah, we wanted to talk about memory. So this talk is a quick way or a mention of many things that can go wrong with memory. It is not going extremely deep into any of them, because what could possibly go wrong is this can go for days, especially with Java and RAM. We'll start with, well, where do bytes live? Or, well, everybody knows that they live on RAM sticks, which are now very much more valuable. Luckily, screenshots of them and pictures of them are not. And how do I read 1 byte is a question that some people find quite surprising, because if you know, you know, but if you don't, you do not read memory as a single byte. You read a cache line and then you mask so that you get exactly what you wanted, which has some interesting consequences. So 1 byte is already a complex operation. You always get a chunk of them. Byte effectively is an illusion. And why does it matter? How is it related? Well, it's very simple. CPUs have many cores. We all know that. Your phones have many cores in their processors, and they have many cores, they have many threads, and they also have a memory bandwidth sometimes published, which is good, but it's also not really that spectacular if you look at it over time. Because this example CPU, which is a very old Intel, and I'll say why I'm picking on old Intels in a moment, 60 gigabits per second of total bandwidth, which means if you do the division, it ends up being roughly 6 gigabytes per core. Then we look at a newer CPU, bigger, more cores, more threads, and memory bandwidth is 4.8, which means it didn't really grow. And then we keep going, and then we see 4.8, and we see 625. So where's the progress? And if you don't see a progress, you would be absolutely correct, because there is something called the processor memory performance gap, which means that processors grow in the performance through optimization and through adding cores much faster than memory is getting more bandwidth. And we have a couple interesting effects because of this. One of the effects is new generations of DDR. More bandwidth, lower power consumption, great. We also get workarounds, more channels, so that you can read more and read it faster, because everybody needs more bandwidth. We also have some unexpected effects. Sadly, Intel documentation pages no longer publish memory bandwidth for new CPUs. I do not know why, but it's a shame. I think it's an opportunity for improvement. And obviously, since recently, DDR prices have increased, and other prices of other things have also increased. And for anybody working with Java, you probably have heard jokes, attacks, appeals to Java and about how much memory it uses, or that it should use less memory, and so on and so on. I am not unhappy with how Java approaches memory, but it's certainly been a theme. So, in Java, we enjoy something called garbage collection. I think everybody knows that. And garbage collection is an absolutely amazing thing. It's basically an automated process that quoting an earlier talk from JavaOne, offers the illusion of unbounded memory, which means it's super convenient. Or if you have programming languages in which you manage memory by hand, you don't have to do it in Java because it happens automatically, automagically even. And it happens reasonably fast, which means usually you don't have to worry about the performance of that. So I can say very dry jokes like that, but there is a couple of problems in Java that people probably have seen. Like the most famous one is Java lang out of memory error, Java heap space. I don't think there are too many people who have programmed in Java and have not come across that, but it's there. So why does it happen? Because there is not enough space available in the heap. Maybe somebody tried to allocate something that's too big. But why do I mention it? Because there is something connected to the heap size. So the heap has a limit, heap has a size, and there is a lot of people who do not set that up, which means JVM will run happily with the defaults. And they don't know what the defaults are, and they are surprised that it runs with the defaults, and the defaults are what JVM has chosen. So a recent JDK documentation page says that, first of all, the VM will consider a machine as a server if it has 2 or more processors and more memory than 1792 megabytes. This, therefore, is a server. What are the consequences of such choice? Maximum heap size is going to be a quarter of physical available memory. If you're running in a VM on a cloud provider of your choice, and you've asked for X gigabytes of memory, and there is only one Java process running there, and you have not set the heap size to anything, it will take a quarter, which means the rest is not going to be used, which might not be what you're after. So JVM ergonomics are a thing. Again, the value is repeated if somebody wants it for some reason, and then 2 cores. And then somebody could ask, hey, but I'm running in a container engine of choice, probably Kubernetes or something else, and then I get a fraction of a CPU, or what really is a CPU? So if you're being allocated millicores, the math is very easy. 1000 millicores makes a core, and if you have enough for it to be visible as 2, then it's 2. And you could think that this translates to a physical core very naturally. Yes, but not always. There are some caveats. Some cloud providers will have, for example, 2 virtual CPUs per core by default. And that's a quote from GCP's documentation. So check your platform, because the memory will map to memory in a normal way, or the way you expect it. But cores and physical cores might not map so clearly. So do check it. Another important thing is millicores is an expression of quota of a CPU. So how much CPU time is a certain workload given in a unit of time. It doesn't say how exactly. So it can be an allocation of 8 physical cores in a very short burst, or it can be 1 for the entire duration of something. If the maths adds up, that is fine. So this is useful to know. And also, Java, the process, has many supporting threads that also need to run. The compiler thread, garbage collector threads, some finalizers, anything else that is there. If you do JStack or list threads, you will see that there is quite a lot of them. It is hard. It is possible, but you have to do some tweaking by hand for your runtime to tell them apart from your application threads. And mostly what we care about is application threads having the ability to run, because if they don't have the ability to run, then the application feels dead or not working. So there is that. And obviously, running in containers now is a solved problem. I don't think I've spoken to anybody that uses Java 8 at this conference anymore, which is awesome. And on the topic of containers, there are some flags which allow memory sizes to be expressed as processors, so that you can tell Java, rather than a specific value, to use a percentage of available memory in the container as limit. And you can also tell Java how many processors it should consider as the count Why does it matter? Because sizes of thread pools will use the core count as their input to size appropriately. That means fork join pool, that means thread pool for running virtual threads, that means all of the other pools that you might have there. People very often do runtime get available processors and size it as an initial size or a target size of a thread pool. That's a very common thing. And if you want to set it to a specific thing or make Java think that there is a specific number there, then there is a flag for that. The percentage flags for memory are useful, but I'm not a huge fan of them. Because rather than saying 60%, I prefer to know exactly how much memory a certain process is going to take. Also because if you're running somewhere, you probably are not running across all of the image sizes and all of the machine shapes in your cloud provider of choice. You probably have set it to a limited number, which means you can do the maths and you can then have an exact value that you run with so that you know what to expect. Because it's much easier to reason, hey, we have 2000 megabytes available, or rather than 60% of visible memory, because then you have to do the maths every single time. It's just nicer for a human. And then, of course, Java is aware of C groups and other things, so this is just to show it. So the first observation or recommendation actually is set your XMX. If you're not setting it, do set it, because the defaults might not be what you're after. Probably are not. And which one should you go for? If you know what the shapes that you're running on, set it to a specific value. Why? Because if you have set it to a specific value, then you are going to have less surprises. Because then if something gets exceeded, it's a specific value that was exceeded and you don't have to do the maths and worry about it. Another observation is Java likes to have more than one CPU. Why? Because of those supporting threads. So giving 50 millicores, so 0.05 of a CPU, is not going to be that great because garbage collectors will try to run periodically, and the compiler threads and all of the other things. And this is what they will have to compete for the CPU given. So ideally, bigger runtimes, and probably less of them is what I would say. Also, another observation is Java likes to have a reasonable amount of RAM. If you need a process that has 64 megabytes, you might observe interesting behavior with Java, and it will probably run. It will likely run, but it's harder. If you need to operate in that realm, Graal is great, but if you're getting big VMs, and right now a lot of people are getting decently sized VMs, give the memory to the Java process and it will run happy. Or in other words, there are no prizes for not using the RAM that you already have paid for because you have gotten that big machine. And why do you get the RAM? Because you also have to get the CPUs and then cloud providers and so on. Tiny amounts of memory, explore Graal. And you can set this value to a specific thing if you run on something that has maybe fractions, or you want the pools to be set to something very specific. XMX versus percentages, we discussed it. XMX is nicer, and I prefer it. So, some almost live demo proving that you can tell Java to think that it runs on whatever. As I said, happy to share the slides. This is to show that it works and those options, which option takes precedence. And since I mentioned flags, I have to mention this one. XX print flags final. This is an absolutely amazing flag that will make the JVM print the total set of every flags that it is using, which means you know what you're running with. But you could say, hey, I've only set up this one and that one. And yes, but flags have dependencies, and sometimes flags override each other, and some flag combinations are incompatible. So if you want to know what is the final set after interpretation and setting of things, you can get it with that option. Some people like to set XMX to the value of XMS, with the expectation being if I set the minimum heap size to X, or to a value, and the maximum heap size to the value, Java should get a stable heap size, and life should be better. And the intuition is correct, but it's not enough. Because in order to get that, you have to remember that operating systems, or Linux specifically, is lazy. It will give out pages to a process when the process tries to use them. Which means if you don't pre-touch, Java process will ask, can I get 2 terabytes, dear OS? And dear OS says, of course, you will get your 2 terabytes whenever you need them. Everything will be happy. If it's not actually used, then this is not going to get allocated, and that might delay a problem. In order to get a stable heap, plus always pre-touch and minus adaptive size policy, because laziness of the OS, that is going to impact start of your process a bit, because all the pages have to be touched. And this has to be disabled, otherwise these defaults are as follows, from when I checked the sources, which means Java might try to give memory back to the OS, even though you don't expect it. But I mentioned clouds and Kubernetes, and I mentioned Java. So some people say that any problem becomes a new problem if you add in Java to it. For example, this person. But also if you add in the cloud, in your cloud provider of choice, and in your cloud runtime of choice. First of all, I like to say that I like glibc, because I get less problems with them. And there are some things which work on glibc, and there were some things that didn't work for me on Alpine. I'm not saying that this is impossible to get them to working, it's just I don't want to spend the time. So if you're getting strange problems, or you want an excuse to be lazy and not try to find for the extra few megabytes of a Docker image, glibc is absolutely fine. Who has had that experience? Probably many people out there. It's a surprise when it happens. There is something called the killer, or out-of-memory killer. You will see pod or container status as killed, something like that. What does it mean? That your workload, your container, was terminated for exceeding the memory limit. Which means the math between the hypervisor, the runtime, and the thing running, that doesn't agree. And this is why I like specific values, because if you need to figure out this math, it's much easier to go and do adding of specific values, so specific XMX, for example, to other things. But one thing that I have seen with some people looking at the Java process, I've said I have a 2 gigabyte limit, for example, for a container. I set my heap size to 2 gigabytes, and then it dies. And that's surprising to people sometimes, and it shouldn't. So let's look at what are the spaces that a Java process uses memory for. There is a couple of them. They come in colors. Sizes are not indicative of anything, and I do mention symbols out there. We will not talk about them, and we'll talk about all the other. First of all, the heap. Heap, where objects live, but every heap has a bit of an overhead. And how much overhead, I will not say. There is no rule of thumb that I am going to use. I am going to show you a slide from last year's JavaOne. And those sizes differ, and they also differ by the JDK version. Which means there is going to be an overhead, and it's not a fixed value, and it depends on garbage collector used and on the version of Java that you run. And usually, of course, upgrading Java is a great thing to do, because you are going to probably get less overhead. But as we can see on the slide, it's not always, but the overhead is there. So there is that. There is the heap. What do you do if you have a heap problem? Well, you take a heap dump. How to take a heap dump? I assume you know. If you don't know, this is one of the popular options. Dear Java, please take a heap dump if you run out of memory. And it works really well if you do it on a laptop, on a VM or somewhere, but if you try to do it in the cloud, you might run into problems. Because, well, there is a couple of them. First of all, you can ask Java to gzip it. Convenient if you want to shave some bytes of a network storage or somewhere. How do you take one? JCMD right now is a very popular way. How do you use JCMD? Everybody knows that, and now everybody has seen it, so now everybody knows it even more. I mentioned caveats. Why caveats? Because if you try to do it in the cloud, you might run into a problem. First of all, where do you put that data? If you were running in a container, you need a volume to which you can ship it, which means you probably need to talk to your SRE people, to your ops people to maybe adjust it. That needs to happen. Second problem is, if your workload is having a health check, heartbeat, something that expects a repeated response in a specific amount of time, taking a heap dump is going to interfere with that process. If you have a very large heap, it's going to take a while for the dump to be aggregated and produced, which means your application might miss that. What happens if it misses too many health checks? It gets killed, which means you didn't manage to get a heartbeat with success, which means you need to take it out of a health check group, or maybe do something to the configuration of your health enforcing machinery so that you can succeed in this. Some people were surprised. If you know it, you know it. But then there comes another caveat. Private data and heap. We all care about privacy, but if we need to debug a memory problem with the heap, then if there are maybe not passwords, but personal information flying in there, looking at it can be suboptimal. What can you do? Well, luckily now we have some choices. I do not claim this list to be exhaustive, but there are two tools which I will mention out aloud. One is from PayPal, one is from an individual that can mask some data in the heap so that all of the memory in there you can analyze, but at least you will not see things like names, addresses, other things that you probably don't want to be looking at. That also makes auditors happy, or happier, because happy is hard. The other one is a new thing, or I learned about it very recently, and it's command line. And I like command line tools because it's very easy to, for example, connect them to an agent, expose them as skills, and then you can ask AI and have AI help you troubleshoot the heap analysis. Maybe you want to automate something in there. So assume you have a heap dump. How do you use it? How do you open one? How do you analyze it? There is a bunch of tools that I will mention here. And I mention many for a reason. We'll talk about that in a second. If you've never done it, I would say Eclipse Memory Analyzer is a free and open source tool that is a really good starting point. IntelliJ can do it, profilers can do it, Visual VM can help you analyze a heap dump. There are command line tools. There is Microsoft GC Toolkit, which is quite nice. It was even nicer when it was Sensum, but we're no longer there, sadly. Caveats. A heap dump from a big heap might be bigger than you expect. So a 16 gig heap, theoretically 16 gigs of memory, good, but we also have the other spaces that we need to put there so that the heap dump makes sense. Some tools like to fail on some heaps. This is why I mentioned many of them, because if you're just hoping that one tool will always work, sometimes it doesn't, or sometimes one tool is just easier to solve a certain issue. Try some, see which one you like, see which one you enjoy and works with whatever you're using. You might need to adjust heap dumps, heap analyzers, heap as well, because if you have a very big heap, you will have to. And then loading a very large heap dump can take some time. Some time as in, it can be minutes, it can be hours, for something very, very, very large. And that's the thing. So, now that we have one, we've managed to open through a tool of the choice. This is a screenshot from the Eclipse Memory Analyzer. We have a couple of options there. We can get a histogram, we can get a dominator tree. So histogram, how many instances per class are there? What are the biggest objects? What are the most expensive objects? All of the tools will show you very similar things. So the tool of choice will not limit what's being available to you. So you can see things like, for example, there is a lot of strings there, and there is something there, and if you've done it, this is going to look very similar across all the tools. Then there is a command line tool, again, called Java Object Layout, which can give you some analytics. And I mention command line tools because it's easy to hook them into AI machinery, which means it's easy to automate that process. Or maybe if you have a crash in the cloud, you can do some pre-processing so that your analysis is faster. As you can see, number of duplicated string instances, same result, same problem as before. What else? What are the other popular reports that we might see? Zero-length arrays, duplicate objects, duplicate strings, some possible leaks, some inefficient primitive data type usage, hash map, hash code distribution, and so on and so on. There is a lot of interesting information that you can get from a heap, and it is quite easy. And just to show that other tools show similar things, those are the options provided by Java Object Layout. So what do we see here? Some stats, again, so many bytes, and so on and so on. And it's all good and happy if you have a classic Java code base and there is nothing strange happening in there, but sometimes you get problems like this one. There is a lot of strings there, and this is the code that makes them. Does anybody see the leak? One person who already knows the answer, you win the prize of, sadly no prize, so there are no Scooby treats to be handed out, or Scooby snacks. The problem was that the native part that was interacting with the JVM forgot to deallocate. What it results as is those objects will be held forever. Somebody might run out of memory. I think that was one of the most surprising ways to generate memory problems with the JVM, because it's not, you have to look at the code to correlate it, because otherwise it's hard to find the source. But that was just a quirk. So in the recent JVM, or recent JDK versions, specifically 24 and 25, we got something which is very exciting, which is compact object headers, which means every single object that is on the heap has a header, which is some amount of bytes that does some bureaucracy. What was the class pointer and some flags stored in there. This JEP has brought us a way to reduce the size of that constant price, which is per object, by some amount. Does it bring a lot? Depends on your perspective, but overall, the win is great. And if we remember that the very limited resource is, apart from memory size, is the memory bandwidth. If we have to shift and move less memory all the time, that's always a win. That's a very nice win. The caveat is this is not enabled by default, so you have to enable it manually, and you have to be on a recent JDK. I am using that in prod, and I am happier. And I have seen this to impact performance in a positive way by some percentage points. Single digit, but still. Yeah? Are there downsides? Sorry? Downsides? So the question is, are there downsides? I have not found downsides. I wish this was the default. I am not aware if it's going to be, or when would it become a default. That's a question to the JDK team. And downsides, not really. Or I have not found any. So there is that. But we mentioned other colorful squares, and Java is not only heap. We already know heap and object headers are there. There's a GC overhead. What else is there? There is obviously metaspace. Metaspace, which is where the classes live. The catch about metaspace, or if you get unkilled, metaspace might be the source of your problem, because by default it is unlimited. I would recommend to give it a value, so that if you exceed it, you get a very strong signal that you've exceeded that, and then you can increase the value that you set it to, because then you know what you're running with, and you know that this is not going to run away, or you will see a crash. What else is there? There is off heap. I know some people in this conference are huge fans of everything off heap. What is off heap? The simplest way to say is memory which is not subject to GC, such as byte buffers. The interesting thing about byte buffers is they have a limit, which is great. Another interesting thing about byte buffers is they limit by default to XMX, which means, is that what you expect? yes, no, maybe answers might vary, but you can set the limit of direct byte buffers explicitly and independently of that. What else is there and how would you track it? Excellent question. The answer is, for example, you can do Java native memory tracking, which is a great feature that tracks allocations in the JVM, which is also a great feature that tracks allocation only in the JVM code, which means if you're using JNI or something else or have native libraries that you use, you're going to miss it, or this tool is not going to surface that information. And there is a small penalty for doing that. What else can you do? Ideally, use Async Profiler. Great tool, open source and free, and this will give you an insight into everything. Or you can, for example, use a custom allocator like gemalog and ask it to generate some log information, and then it will give you a way to find the problem with native memory if that's what you use. And speaking of native memory, there is another thing that I have to mention, which is trim native heap interval. You can control after how many milliseconds JVM will attempt to trim the native heap. So JVM can look after that. And there is a caveat here. This option is only supported on Linux with GNU C library, so glibc. One of the reasons why I like glibc more than Alpine. How else can you trigger that if that's the problem that you suspect? There is a JCMD option to do it. So there is that. And then there are thread stacks. So obviously every single native thread needs some stack size. And then I have heard people who say, you're running X amount of threads. Every thread, we're going to calculate it as 2 megabytes always. And there is a problem with that approach. First of all, you can configure how big your stack can be. But another great thing about Linux, again, is it is being lazy. So a thread will only consume this stack size if the stack is really that deep, and it needs to be that big. So it is certainly possible for threads to be less bad. But if you have very deep stacks, some frameworks are definitely guilty of that, they will take more memory. And because we have Loom, we have virtual threads do not manifest themselves like that. Virtual threads, they store their state on the heap, and when they are using a carrier thread, the carrier thread naturally is going to be a native one. Symbols, I promised not to talk about. And we're going to mention code cache. Code cache, so the space in which compiler is going to store the bits that it wants. You can print code cache statistics when the JVM process exits. You can ask it to be emitted at other intervals. There is more options, obviously, than this. Why do I mention that? Because there is an initial and there is a limit. The defaults are 160 kilobytes and 32 megabytes, respectively. And is it a lot? Is it not a lot? My answer is, if you have a very big, sizable code base, you load a lot of libraries, and your process runs for a very long time, 32 megabytes might not be enough. So it is very useful to check the stats and see if code cache is enough for you. Also, how much code cache is being used depends on JVM version, because there are new optimizations that keep coming, which is great. And if somebody's on the JDK 25, specifically, there was a bug that relates to code cache, which was fixed in 2502. So if you're on 25, please upgrade. Or maybe 26 is most likely free of it. So we talked about sizes. What else can we talk about? Well, memory throughput we have seen. What about application throughput? Application throughput is the time the application spends running application code, as opposed to garbage collector and other things. So you probably have all seen a graph of how much GC time is being taken versus what the application is doing. And with that chart, there is this classic error, GC overhead limit exceeded. I assume you've seen it. What it means is garbage collection has taken too much time in relation to the application time. Sounds great, but there is a catch. The default is, for the limit, is 98. So if GC runs for more than 98% of time, so your application only runs for 2%, only then this will trigger. Is it a reasonable default? It depends. But if you care about your application liveliness, you probably want to adjust it, because you probably want your application to throw this earlier and fail faster. Or you can completely disable that check if you have a very long running process which just has to finish work and you don't really care about the wall clock time, and if GC has to run, then it has to run. What else would I say? I would say enabling GC logging in production is quite good. We are in the modern world. I will not mention what incantations to use in JDK 8 anymore. One thing, disable explicit GC, a very useful flag. If somebody likes putting system.gc in the code base, that means this will become completely moot or useless or not effective. Some people try to outsmart the GC sometimes. Some of those approaches are valid, some are not. It's up to you to decide, but there is a flag to disable it. Which flags to use? Probably this is a very good, or this is probably one of the best references for it. And what I have to say is, do watch out for slow devices when you're using GC logs, because this has been a source of very nasty surprises. So if you want to, for example, write a GC log to a device that you don't have write permissions to, something might not work, or a disk that is exceeding its IOPS or something else, it might lead to surprises. And you might actually observe crashes because of this, and that's not great. So what could a GC log tell us? Well, we can look at one. Naturally, don't read this by hand, because life is too short. So examples are just that. There is a ton of analyzers out there. Some are free, some are less free. Which one is good? See which one you like. If you work at a company that is here on the list, I'm happy to see that you recognize and you're happy. They will show you similar things. They will show you how GC is working. Does it need help in any way? But if you want to play with GC flags, you will end up in a very interesting world of flags. I already mentioned print flags final. And with flags, I have to say, flags can change between releases. And there are two ways in which you can find all of the references. One is JDK sources, which is obviously great. There is also source number 3, which is your colleague, which knows all of them by heart because they are such an expert, if you have one. And there is a very nice website of Crisco code. So something which I very often use as a reference for JDK flag options, which has explanations, defaults, which JDK version it applies to, and so on and so on and so on. And in there you can find something like, for example, XX on out-of-memory error, and you can give it a path to a script, and you can see that this is available in those JDKs, and so on and so on. And you can, for example, if there was an out-of-memory error, execute a script that will do something, and that's now up to you. That one we talked, that one we also talked about, that one we also mentioned. But hey, we've analyzed the flags, they seem to make sense, application is not crashing, so we're no longer getting unkilled, everybody's happy. Why could my application be slow? Is there something in the heap that very often is the source of that? And I will mention two things here. First of all, lots of strings. Why lots of strings? Maybe because JSON, maybe because LLMs, maybe because something else. Java has a great feature called string deduplication. So a GC scan the duplicate strings. If you ask some LLMs, they will tell you something which is not fully accurate around it. But most of GCs, or all of the GCs, if you're in a recent version enough, can do it. Is it a magic silver bullet? No. Can it save you? Maybe. Should you use it? I refuse to answer. You have to try, and you have to see whether. So I've seen both situations in which this is a great option and it absolutely should, for some applications, be enabled. And I've seen situations in which it's contributing latency to the application, it's making GC do more work, and there is really no effect. Why? Because string deduplication deduplicates the underlying array of a string, so it has to do the comparison, which means garbage collector has to identify that those strings are actually the same. And it only does it to objects which pass a specific threshold. Default is 3, and 3 means garbage collector epochs, obviously. But if there is a lot of objects in which the underlying array is going to be the same, you still pay the header price. There is still going to be a lot of objects. So if that's your situation, the option of the solution is different. It's pooling strings and trying to reduce the amount of the ones that you have. And then you could ask, yeah, cool, but which strings? And that would be an excellent question. And I've already shown you the answer. And this answer is obtainable through any heap analyzer out there. You can see which strings and how many are, and how frequent they are present in the heap. And then it's up to you to see, why is this one there so much? Could we do something about it? Should we do something about it? So this is going to be a bit application specific, but you can get really good results. And there are some cases in which if you are allocating string every single time on entry to a certain code path, if you do it, you're not going to get anything useful, because allocating means you use the throughput and so on. Another thing that is a potential source for slowness is wrapper types. So capital double, capital long, capital float, objects which wrap primitives, especially in a collection. So if you see a heap which has a lot of long objects, for example, or a lot of double objects, and so on, it might be a source of slowness. How much can it make a difference? Well, using some sample workload, changing array list of long to a specialized collection has reduced allocation by a bit. The difference is hundreds of megabytes in each time frame, which means that doesn't sound too bad or too good. It's 100 megabytes. That's not a lot. That's nowhere near the memory throughput values that we've seen at the very beginning. However, what might end up happening is that it makes a huge difference to the runtime, because there is less indirection, so you don't have to jump through an object header to the value, because you can use actually the primitive directly. But it also might be that there is no impact, because it really depends on workload. So it can be a big impact, and it can be not a big impact. It really depends on your workload, so you will have to test. But if you're doing collections which have a lot of primitives, then I would recommend some specialized collections. I will recommend Eclipse collections with a logo, because they do have a nice logo. But there are more options out there. If somebody would like to know which one is best, it depends on your workload. So give it a try. You can be happier with any of those libraries, or if you really like coding, you can write your own. The important thing is, because they will avoid wrapper types, you can get a lot of boost, but there is no promise that you will, because it depends on your workload. And there is something that some people say should save us. So maybe if we could get 2 terabytes of memory and just run epsilon GC, so something that does nothing when it's supposed to do GC, which is how you enable it, maybe everything will be faster. And sometimes epsilon GC actually is very useful. But is it always faster? The answer is it depends. This is what really demonstrates how useful automatic memory collection in Java is, because it does eliminate garbage, which means if we have a very large heap, we have less memory to traverse, because the garbage is no longer there. And in a heap which has garbage, useful objects, garbage, useful objects, you have to go through much more space there. And we are getting towards the end, so I can say thank you. If you would like the slides, feel free to drop me an email. I'll be very happy to share. And if you have any questions, we have a bit of a buffer, so we can go through them. If not, happy to talk outside. There is a question. Awesome.
Yeah, so...
Is your question about how you would pass this information to the JVM, or how you would size it?
Should you even set it?
Should you even set it?
And is there a benefit or,
Is there a benefit? So, yes, if you would like to get all of the thread pools sized to a specific value, because maybe the default is something that you're not happy with, or maybe the default is too much, or maybe you would actually like to have those pools bigger because your workload will be happier in that way. If any of that is the case, then I would override, because the default is, as you said, is going to see what's given to it. But I would expect the information, if you pass it through the flag, to be actually reflected. That was in one of the slides. You can see which one takes precedence. It is visible. It is the value used by the JVM. If you'd like to talk about this more, we can do it outside, because this can be a lengthy conversation. Is there anybody else? There is one more question.
Maybe what's the most common cause for memory problems?
What's the most common cause for memory problems?
I can imagine most of the time it's not on the programming side, or?
In my experience, most of the issues are because of strings, but that's just across the years, and usually something wrong is happening there, and because especially if strings are being mutated, that means all of the arrays are in memory, and then that leads to exhaustion, and that leads to excessive memory pressure, and we get a 3-minute sign, and I'm perfectly aware of it, because we're already in the questions phase. But there is that. With JSON processing, strings again, but it can be anything. As in, I wanted to show with those rectangles that memory problems, it's a simple thing, and it's also a surface that has many points from which you have to look, because there is so much involved. Native memory is a source of surprises, because people forget that byte buffers are there. If you're using, for example, Netty, it will use some native memory, and you have to account for that, which means you cannot size the heap to take the whole container, because then it's going to run out of memory. That's one of the often other surprises. I think that's probably what comes from to the top of my head. I think we've exhausted the questions, which means thank you very much. Have a great day. Enjoy JavaOne.